show on the road. We're in a section that takes a lot of time just to do one question, so oops, I just realized something. There we go, get some light. That's the guy that we left off at last time, right? This cubic function. We found the first derivative and we used it to find when a function was increasing, when it was decreasing, and still got the notes here. Remember doing this, local max, local min, all that good stuff. And first derivatives tell you a lot about a function, right? Tells you all this stuff. What we're now going to do is use the second derivative. Now, the first derivative will tell you about things increasing, decreasing. It'll tell you where the local max and mins are, and that there are a local max or a local min, right? It'll tell you all of that. Second derivative tells you when something is concave up, concave down, right? So when it's a happy face, when it's a happy face, right? Concave up, concave down. And it will also tell you where points of inflection are. That's where a concave up changes to a concave down, right? And so that's not as useful in my opinion, right? The first derivative tells you a lot of good stuff. Second derivative just like fills in the gaps. And so let's see how the process works. The good news is it's exactly the same process as we did for the first derivative. So I'll differentiate the first derivative and I'll get 6x take away 18. So that would be my step 1. You then have to find the critical numbers. Well, the critical numbers of a second derivative are when the second derivative is 0 and when the second derivative is undefined. Would you agree that 6x minus 18 is never going to be undefined? So I'm only going to need to find second derivative equal to 0. And do that in my head. The answer is 3. So we found the critical numbers. What we do now is we create a number line. And that number line is going to be used to record what the second derivative looks like at little snapshots of its life. Well, x equals 3 is very important, so I'm putting that one in first, putting a nice dot there, and a big 0 on top of it to tell me the second derivative is 0 there, and then just continue the number line as much as I want. And at this point, to complete this table of signs, or really it's more like a line of signs, don't I pick a test point from this region and another test point from that region? And all I'm interested in is plus or minuses. So you don't need to be too detailed, is it plus 42 or plus 4? If you're really bad at arithmetic, you'll probably still get the right answer, right? You'll still say it's plus, maybe the wrong amount of pluses, but you'll still say it's plus. So I'm going to do this in my head. If I do a test point, oh, here's a point. Any one of those numbers, right? In fact, 1.2 would work, but nobody should do that one, right? So which one of these guys do you think I'm going to pick because I'm lazy and I don't want to make a mistake? Which value of x on the left here do you think I'm going to choose for my test point?
0.
0. And would you agree the answer is negative 18, so everybody's negative? Do you know, see how quick that was? I really didn't need to do it at all. I mean, in this case. So over here, you're going to have problems. But, yeah, how about 5, right? 6 5's take away 12 is a positive answer. I don't care what value, just that it's positive. Right. There we go. We now need to interpret this guy. So, right. If the second derivative is negative, it is concave down. If the second derivative is positive, it's concave up. That's easy to remember for me because it sounds like it's going the right way, right? Plus is up, negative is down. Doesn't that kind of feel right? Plus is up, negative is down. So here goes. This function is going to be concave upwards from 3 to infinity. And it's going to be concave down from negative infinity up to 3. And that's that done. And all I need to do now is point of inflection, right? The point of inflection is when there's a changeover. A changeover happens here. Would you see it? So there's going to be a point of inflection at x equals 3. And that gives me coordinates, because very often they want to know the coordinates of the point of inflection, not just its x coordinate, but its x and y. So where do I get the y coordinate for this fella? Do I use this function at the top? Do I use the first derivative? And do I use the second derivative? Which one do I use to get this fella?
3x squared minus 18x plus 24.
Now, that guy is the first derivative, isn't it?
Yes.
And we're really wanting to know the coordinates on the original function.
Oh, sorry, I didn't see that this is from the previous question up at the top. So yeah, it's from x to the third minus 9x squared plus 24x minus 8. So that's how you get your y coordinate.
You nailed it. Bang on. So I'm doing it slow because I can't type very fast. There's the first guy. Take away 9 times 3 squared. Well, I'll do that in my head. Plus 24 times 3. And then finish with take away 8. And so the answer is 10. So we've pretty much done what we need to do. Just using derivatives, haven't I found that when it's increasing, when it's decreasing, that it has a local, that says max by the way, at 2,12, a local minimum at 4,8, it's concave up, which basically means it looks like that, and then it's concave down, so it looks like that. Right. And the place where the changeover happens was at x equals 3, right? Now I'm going to take well, I won't take all of that. I am now going to draw in Desmos this guy, and we're going to see if everything that we said here actually matches what the graph looks like, because that's way of checking, isn't it? Especially in a test. And so if you want to bear with me for a second while I switch over to here. Here goes y equals, and it's going to be an x cubed, take away 9x squared plus 24x, and nobody noticed that I was in capitals, or at least they did. They forgot to tell me. Ah, it's getting worse, not better. Oh dear. If I had a brain, I'd be dangerous. And there's a minus 8 at the end, I believe. Okay. Now, when you do something in Desmos, that doesn't look very much like anything that we've got, but that's because our X and Y windows aren't very aren't in the right place. So I'm going to hit this fella, and from what I can see on all the numbers I've got here, as long as I do an X, say somewhere between -1 and the biggest thing that happened was at 4, so let's say -1 to 5 on the X's. That's something. Oh, and now I need to do the Y's, of course. And the Y's, well, I think the biggest number I had is 12 here. So I'm going to put in -1, that way I can see the x-axis. And I'm going to go 12. Okay, maybe shrink back a little bit. There, do you see you have to sometimes tweak the X and Y's, yeah. Right, let's check it out. According to what I had in my list here, there's a local maximum at 2,12. Would you agree that works? It's exactly what I said it would be. There's a local minimum at 4,8. Would you agree that's exactly where it is? Would you agree that it is increasing up to here, then decreasing here, and then increasing again? That's what I said in calculus, and yep, it works. Would you agree? Well, it's a bit harder to do, so what's that, 310? So at that point there, oh, come on. Can you pretend that says 3,10, because I can't seem to get it exactly in the right place. Isn't that where the point of inflection was? Can you see the concave up and then the concave down? One on the left is concave down, on the right. Everything I did there. Now, if the unscrupulous amongst you are thinking, oh, this is going to be easy, I won't do all that hard stuff. I'll just put that in and write down the numbers in my homework. And you probably could. And when I give you the final exam question, you won't have a clue what to do. Because if all I get is an answer and I don't get the math that backs it up and the table of signs and all the good stuff that belongs with that, then I'm just going to assume that you did that, right? That you just went to Desmos, put it in and wrote down what you saw. And this class is not, I know how to use Desmos. This class says, I know how to prove things and use calculus to prove things. So it's a totally different mindset and a total different skill set. So do not get into the bad habit of saying, well, I can do all my homework dead quick. I'll just plug it into Desmos and write down what it's, what it says. So pretty cool. It worked. Now, one of the advantages of calculus is, can you imagine one of those x coordinates where a local max happened to be the square root of 2? You imagine that, right? X was the square root of 2. If you use Desmos, it won't tell you that. Won't it tell you it's 1.1412, 3.4567? That's another clue that I will know that you've not done it right, that you've just done it basically by using a picture. So, time to move on. That guy that I've just done is representing every polynomial that you're going to get. Obviously, there are many versions of polynomials, but the process that I used is going to be it. Next fella I'm going to be looking at is going to be a fractional power one. Right. So the guy that looks like that is question 9. Okay, we are going to, in this particular question, only do increasing, decreasing, maximum. In other words, we're only going to do the first derivative part because that's all they ask for. So, would you agree that this is a product rule? So, it's going to be f dash j plus f of j dashed. If you differentiate x to the 2/3, you'll use the power rule. Multiply by the power and reduce it by 1. Leave g alone. Plus, leave f alone and differentiate that guy. The algebra in here is going to be really ugly, but we just have to live with it. If you multiply this guy by this guy, you'll get 2/3 x to the 2/3. If you multiply this guy by -6, you'll get -4 x to the -1/3, and then you have x to the 2/3. I'll then add these two guys together, and now I have 5/3 of this fella, take away 4x to negative, God, that looks weird, to -1/3. Are you comfortable with what I've just done? Right, first derivative, product rule, ugly fractional powers, live with it. You really need style points here, which means I'm going to have to factor the heck out of this. And I think we're getting, well, the more we do, I think we're going to get more comfortable. Would you agree x to the -1/3 is the common factor? Right, I got 2/3 and then -1/3. So I'm going to pull out x to the negative 1/3. That's going to leave me, well, let's do this one first, minus 4. Now, you're going to have 5/3. If you have 2/3 and you remove negative 1/3, you're essentially adding a third. 2/3 add a third gets you x to the 1. You comfortable about that? Now, I'm going to make it a little bit different, but only a little bit. I'm going to move that 1/3 power down to the bottom. And there's a reason for me writing it that way. Technically speaking, that is style points. That's totally allowed. But I'm changing it just a little bit. What we need to go hunting for now are critical numbers. We're going to look for places where the derivative is 0, and we're going to look for places where the derivative is undefined. Let's do when the derivative is undefined. If you have a fraction, aren't you only going to be undefined when the bottom is 0? And would you agree x equals 0 does that? Are you comfortable about the x equals 0 being an undefined value for the derivative? Now, when are you equal to 0? Well, a fraction is equal to 0 only when the top is 0. It doesn't matter what really is going on at the bottom. So we need to solve 5/3 x take away 4 equals 0. If you add 4 to both sides and you divide both sides by 5/3, which is the same as multiplying by 3/5, can you trust me that there is your second critical number? Any problems so far? Ugly derivative using product rule, factor the heck out of it, make it a fraction. Find out when it's 0, that it happens when x is 12/5. Find out when it's undefined, it happens at 0. Now, if you did not do the style point line, right? If you didn't do this guy, I'll try to hide it. If you did not do that guy, if you just got to here, and I said to you, okay, time to find critical numbers, you might be able to figure out 0's a bad value, probably because of this term. Would you agree you probably wouldn't have found the 12/5 easily? Okay? Knowing that 12/5 is when that derivative there is 0. It's much cleaner, isn't it, when it's factored? So there's a reason, another reason for why style points work. So what we're going to do now, basically to finish this question, is we're going to do a table of signs. And I'm going to put x equals 0, which is here. And I'm going to put a little circle around it. And I'm going to put un, meaning that the derivative, because this is a first derivative, is undefined there. And 12/5 is like 2 and 2/5. So there's 1, there's 2, there's 3, I guess there's 4, put a negative one over there. And roughly, I'm not saying this is exactly in the right place, but that's where 12/5 is. So great. So do you see that the two critical numbers have now separated the number line for this first derivative into 3 regions, right? A guy over here, a guy here, and finally a guy over here, right? Boom, 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 boom. So I just need to do some test points. And I'm going to pick -1. I'm going to pick 1, and I'm going to pick 3. Does that seem like reasonable? Pick that guy, pick this guy, and I'm going to pick that guy. And what I'm going to then do is I'm going to evaluate the derivative, which is this guy, at each of these points, and I'm going to find out if the derivative at these points is positive or negative. And I don't care which it is. That's positive. That's negative. And that's positive. And you can go and check it yourself later, but I know that's the case. So we have positive here, negative here, positive here. If anybody is wondering how was I doing that in my head, because you know I can't count, I cheated. So let me show you the cheat. -1. Right, now if I put in -1 into here, it's a really ugly calculation, especially at the top, but that's not what I did. I just said to myself, 5/3 times -1 is negative something. Take away 4 is still negative. So I know the top thing is negative something. And isn't -1 cube root of -1 also negative? A negative thing on the top divided by a negative thing on the bottom made that answer positive. Now, when I did f of 1, I went and said, okay, 5/3 take away 4 is negative. 1 cube root of 1 is positive. A negative on the top, positive on the bottom, negative answer. And then if you do 3, that's 5 take away 4 is 1. Cube root of 3 is some positive number. 2 positive things, positive answer. So, you know, it's a shortcut. If you want to learn how to do it, you can. Otherwise, don't you just plug into your calculator and do it the other way. Well, we're finished, except for writing down the answers. This function is going to be increasing from -infinity to 0 and from 12/5 to infinity, right? Positive derivatives. This function is going to be decreasing from 0 to 12/5. Now, at this point here, where there is a 0, you see this guy here? Right? It's -0 derivative positive. -0 derivative positive. So I've just figured out that there's a local minimum. And it's going to happen at x equals 12/5, and the coordinates of it are going to be 12/5, 42, because I'm just guessing a number for the y coordinate, because I'm just want to do things quickly. But to get the right answer, I wouldn't have to plug it into here and get some really ugly, weird value, but that would be the y coordinate, if you were asked to find it. Now, what on earth is happening here? Well, it could be that there's a vertical asymptote, because vertical asymptotes will cause a derivative to be undefined, right? It might be zooming up, you know, it might be zooming down. Or the other alternative, it could be one of those corners, right? One of those cusps. The honest answer is you can't really tell which of those two situations until you go over here. Would you agree that there is no vertical asymptote in this function? I mean, don't you need a fraction with something on the bottom to generate a vertical asymptote? Since there is no vertical asymptote here, what that is telling me is I've got a cusp, right? I've got one of those kind of things going on, right? Little corner. So bearing that in mind then, it's going to go positive and then it's going to negative. Doesn't that also qualify as a local maximum, right? Just because you're not smooth doesn't make you different, right? You're still a little top of a roof. And so I now have a local max. And that should be at x equals 0. And the coordinates of that point, I can actually tell you the real answer because that's easy. And at this point, I'm just going to call that good. Plug it into Desmos. Convince yourself you're right. Hopefully. So that question is for situations where you get fractional powers, right? The next one we're going to do is rational functions. Before I start this question, you know that you recognize a rational function when you see one in grade. There's nothing too amazing about that. Would you also agree that there's a vertical asymptote at x equals 3 here? Right? X equals 3, there's going to be a vertical asymptote. That tells me that when I do the first derivative, because this question is again only going to ask you for increasing, decreasing, and that stuff, right? It's not going to ask you about concavity yet. You're going to be able to figure out that x equals 3 should appear as one of my critical numbers, and I'll know it's a vertical asymptote. So I'll keep away from thinking there might be a local max there, for instance. So let's see what we have. To differentiate this function, it's going to be a quotient. It's going to be f dash j take away f of g dashed all over g squared. If you differentiate the top, you get 2x, leave the bottom alone, leave the top alone, differentiate the bottom, all over x minus 3 squared. Distribute this guy, you get 2x squared, take away 6x. This guy, you get take away an x squared, take away a negative 8, is add an 8. And then collect like terms. I have an x squared, a negative 6x, plus an 8, and I have an x minus 3 squared. Kind of rush through that a little bit, but I mean, you can always fill in the details later. Style points. Does it look like the original? Check. Have I factored the heck out of it? No. Do you recognize this quadratic can be factored? Anybody want to have a shot at what the factoring or the factors are?
-2, -4.
You agree? -2, -4. So, differentiate. Critical numbers now. When is this derivative 0? Well, this derivative is going to be 0 when the top is 0. So, because I've done all the hard work in style points, won't it happen at x equals 2 and x equals 4? And critical numbers also happen when the derivative is undefined. Undefined will happen when the bottom is 0. And because it's already set up nicely, x equals 3. Remember I went and said right at the start that there's a vertical asymptote to x equals 3. Do you see the derivative has found it as a critical number? So I can now create my number line. And I need to have 2, 3, and 4 in it. So I'm going to start at 0. Go 1, 2, 3, 4, and 5. And I'm going to remind myself that this table of signs is all about derivatives. At x equals 2, there's a 0 derivative. At x equals 4, there's a 0 derivative. And at x equals 3, there's an undefined. In fact, I already know it's a vertical asymptote. Now I need to do some test points. There's 1, 2, 3, 4 regions. So I need 4 test points, one from each of these 1, 2, 3, 4 regions. This one's the easy one. I could pick 0 or 1. I'm lazy, I'll pick 0. And the last one is pretty easy. I'm going to pick 5. What's not so easy is if this is 2 and this is 3 and I have to pick someday that's neither of those numbers, but between it, aren't I going to have to pick some like 2.5? Right. Or any value that you can make in that range. And now I'm going to find the value of the derivative at each of these test points. And since it's the derivative, I'm going to be using that guy, right? Now, I could simply just plug in 0, get the answer, plug in 3.5, get the answer, plug in 5, get the answer, and I would be able to tell you it's plus 42 or minus 7.1, and that's fine. I'm just not going to do it that way. I'm just going to do it the shortcut way. If this is 0, that's negative, and negative squared is positive, that ends up being plus. If I put in 2.5, that'll be positive, that will be negative, that'll be positive, so answer's negative. If I put in 3.5, that's positive, and this guy is negative. And lastly, if I put in 5, positive, positive, positive. That's how quick you can do it if you get fast at the shortcut. Just find what each piece is equal to, but only that it's plus or minus. You don't need to get any more detail than that. And then combinations of plus and minus do that. Or you can do it the way I said, the slower way. Right, what do I know? I know it's positive. I know it's negative. I know it's negative somewhat. And then I finish with positives. So I can now go and tell you the interval of x's where it's increasing, and the intervals where it's decreasing. Right, anything that away, so that would be from negative infinity up to x equals 2, and from 4 to infinity, right? So basically the outsides, it's increasing. Now, in the decreasing side, from here to here and from here to here, don't write this down because it's wrong. Oh, it's negative from 2 to 4. That is wrong. It's actually 2 to 3 and 3 to 4. Even if WebAssign doesn't say it is. And you might say, why? 3 isn't the function undefined. Right? It's a vertical asymptote. If you're undefined, you do not belong in a place where the function's increasing or decreasing. How can you be decreasing if we don't even know where you are? And infinity doesn't count as I know where you are, because aren't some vertical asymptotes both infinite and negative infinite at the same point? So we destroy or don't use any x coordinates where an undefined derivative exists. So that's the right answer. Now, in this story, there are going to be some local max and local mins, but not at 3. Isn't 3 a vertical asymptote? So I'm not going to look at it. On the other hand, at 2, I have a function that is positive, 0, and negative, which is a local max. So there's a local maximum at x equals 2, and its coordinates. This is not correct, but you'll find the real one and you plug it in there. And what's happening over here? Well, at x equals 4 on the left, it's a negative derivative. So it's sloping down the way. Then it's 0, and then it's positive. And that we call a local min. And that's going to happen at x equals 4, and its coordinates will be 4, 42. Well, whatever the real coordinates are. Anybody's had me before will know why I like 42. Anybody want to tell the others what's special about the number 42? No sci-fi people amongst us.
I don't know your particular reason, but isn't
Uh-huh.
it from, oh, I don't remember the show that it's from, but it's supposed to be the number that explains the meaning behind everything in the universe, right?
That is the one. It's the Hitchhiker's Guide to the Galaxy.
That's what it
42.
was.
42 is the answer to the meaning of life and everything, allegedly. So if someone asks you a question and you don't know the answer, you will say 42. It's a good show. Should watch the British version of it, not the movie. The movie's pretty bad, in my opinion. Right. So we have done polynomials, we have done rational functions. You kind of know there's going to be a theme here. The one that people find the most awkward to deal with, we're now going to do trig. And again, we are only going to do the first derivative stuff because that's all they asked for. The second derivative, the concavity, is less useful. So there's a lot fewer questions that will ever ask you to do concavity. So here we have 5 sine x. Add, oh, interesting, 5 cosine x. And we're only interested in x in the range 0 to 2 pi, which is kind of helpful because it means you don't need to do an infinite number of answers. So first derivative is 5 cosine x, take away 5 sine x. And now we need to find, well, that wasn't too bad. We need to find critical numbers. In this case, I only need to find when is the derivative 0, because 5 cosine take away 5 sine is never going to be undefined. So I now need to solve a trig equation. And trig equations are horrible for some of you. I kind of like them because they're a challenge, because they're almost never the same each time. There's always some identity floating around or some different technique that you need. This guy has got a cosine in it, this guy has got a sine in it. If it had a cos squared in it and a sine in it, I would have turned cos squared x into 1 minus sine squared x, and this would have become a quadratic. And we've seen one where that happened in a different question. But it doesn't have a cos squared in it. It doesn't have a sine squared in it. It only has a sine and a cosine, which means we tackle it in a totally different way. One of a shot at it. How could you do this? No takers? We're trying to find x. That's essentially what you do when you solve any equation. Trig equations have their own little idiosyncrasies. Okay, so I am going to do this then. I am going to, as long as you do it to both sides, it's okay rule. So I am going to add 5 sine x to both sides. That doesn't look like I've done much good, but, you know, bear with me. Might be able to get something out of it. Any ideas what I could do to both sides in my next line?
Divide by 5.
Nothing wrong with that. If you can see a way of making the numbers simpler, go for it. That's a good step.
Divide by cosine.
Yeah. So if you divide both sides by cosines, this becomes 1, and this becomes tan x. And that is good news, right? Because we know how to find the tan of x equals 1, isn't that? Just find a place on the unit circle where the x and y coordinates are the same. And if you imagine your unit circle over here, isn't there one of them there where they're both the same? And there's another one down here where they're both the same. And the angles happen to be pi upon 4, which is this one. Does anybody know what that guy there is? The other one.
7 pi over 4.
You nailed it. Right, did you notice that that one was solved totally different from the sine squared plus cos x one that we did whatever a few days back? I can't remember now, last week maybe. Trigs like that, you know, every trig equation is its own little puzzle, you know, and they don't always end up being the same method for each, right? But we got it, so we're cool, so we're happy. So I'm now going to do my number line. And since I know to start at 0 and 2 pi, I'll just do that because of this. I'm going to put, I think things should be in probably multiples of a quarter, right? So I'm going to have 1/4 pi, 2/4 pi, count it in space. Let me redo that line. For some weird reason, my brain forgot to put pi in the middle. There we go. So I'm going to go 1/4 pi, which is about here, 2/4 pi, which is this guy, 3/4 pi is this one, 5/4, 6/4, 7/4 pi. I think that's a pretty decent scale, right? Maybe even a little bit more than I needed. Over here, the first derivative is 0 at 1/4 pi, and over here, the first derivative is also 0. And so if we look at this guy, would you agree we've got 3 regions that we need to deal with? 1, 2, 3 regions. And so I'm going to do some test points. I'm going to pick 0. Well, how about pi? Yeah. And how about 2 pi? 0 for this region, pi for this region, 2 pi for that region. Anybody in the region will do, but those seem reasonable. And now I'm going to find the derivative at those points. And I'll go up here to the derivative, and if I do the derivative at 0, that's 5, take away nothing, so the answer is 5, which makes it positive. If I do pi, the cosine of pi is -1, so 5 -1. -5 take away nothing, so it's negative, and trust me, almost positive. So whole load of pluses, whole load of negatives, a whole load of pluses. To save some time here, I'll not finish it, but can you tell that it's going to be increasing from 0 to 1/4 pi and 7/4 to 2/4 pi? And isn't it going to be decreasing from 1/4 pi to 7/4 pi? And would you agree that at 1/4 pi it's got a local max, and at 7/4 pi it has a local min? And all of that would get done, and you'd write it down. But kind of, once you've got this guy, don't you know everything you need to know about increasing, decreasing, local max and mins, right? Once you've got to there, everything else is in front of you. You just need to know how to interpret it. Are we good? Even if I've got a couple of others, because they are really long, these questions. So what are we left with? Well, we've done polynomials, we've done fractions, and we've done trig. The next one is just, you know, randomness, right? All sorts of weird combinations can happen. So the one I'm picking is the weird combination this time. Is going to be x to the 6 e to the -x. And again, it's only going to be first derivative stuff, right? Increasing, decreasing, local max and min stuff. Right? So, going to differentiate it. That's going to be f, that's going to be g. I know this is a quotient, a product. If you differentiate this guy, you get 6x to the 5, leave the other guy alone, plus leave the f alone, And if you differentiate e to the negative x, you get e to the negative x. Do you get anything else when you differentiate e to the negative x?
You also get a -1.
Yeah. Isn't it dead easy to miss that guy? I call them baby chain rules, right? You know, so easy to miss it. So what I've got now is a common factor of e to the negative x and a common factor of x to the 5. And if I do that, I get a 6 here and a negative x here. So actually, that was quite a nice, easy derivative. You agree it wasn't too much heavy-duty algebra. I'm going to rewrite it in a slightly different version, like that. You okay with that? Negative, negative. So let's go looking for critical numbers then. Places where the derivative is 0 and places where the derivative is undefined. Right, if you're going to be 0, it really doesn't matter what's happening on the bottom, isn't it only the top that matters? And because that is factored, x equals 0 and x equals 6. So there are two good critical numbers. The derivative is going to be 0 there, right? Now, if you're going to be undefined, you only need to look at the bottom. And is there a value of x that makes e to the x 0? No. So there's nothing. And that means we now have, put 0 there, there's -1, 1, 2, 3, 4, 5, there's 6, 7, 5, 3, 2. And this is our table of signs now. At x equals 0, the derivative is 0. At x equals 6, the derivative is 0. And my test points would be -1. Right, that's in this region. Somewhere in this region, it really doesn't matter, they're all ugly. 3. And someday at the end is 7. And then I would find the derivative at each of those snapshots, each of those test points. And I'm going to do a cheat here. -1 to the 5 is negative. 6 take away -1 is 7, that's positive. E to the negative is always positive. So what have I got? A negative, positive, positive. That makes this guy negative. If I plug in 3, you're positive, you're positive, you're positive. So everybody's positive. If I plug in 7, you're positive, you're negative, you're positive. The answer is negative. Right, let me do one of the shortcuts slowly. Let's do this one. I said it's positive. 3 to the power of 5 is a positive number, right? I don't need to know it's 284, whatever it is. Would you agree 6 take away 3 is positive? And would you agree e cubed is positive? Wouldn't a combination of everybody positive generate a positive answer? That's what I was doing in my head. I just find this quicker than evaluating it as minus 18.123 or 72 and all that carry on, especially when these things get really big and ugly. But that doesn't mean you have to do it my shortcut way, right? You can still do it, you know, by evaluating, and that's fine. And at this point, I'm going to kind of skip by the next, but would you agree that it is decreasing from -infinity to x is 0 and from 6 to infinity, and that it's increasing from x equals 0 to 6, and at 0 it goes down along and up, so that's a local min, and at x equals 6 it goes up along and down. There's your local max. That all makes sense. So we call that one good. So what is left? Basically all that is left is to do a question which you would do second derivatives and find concaves ups and concaves downs. So I'm going to skip the increasing, decreasing part and just go first derivative, second derivative, and just focus on that now, right? So this is question 17. And so the function that we're going to deal with is that guy. And I am going to look at when is it concave up, when is it concave down, and coordinates of any points of inflection that it may have. So this guy's going to be F, this guy's going to be G. And I need a kind of few seconds to get my act together because I know what's going to happen here. When I differentiate this thing, would you agree it's going to be an ugly answer? But that's only the first derivative. Would you agree the second derivative is going to be pull your hair out ugly? Right, so I'm just warning this is going to look messy, and there's just no way of avoiding it that I can think of. It's just going to be messy, right? And let's go. It's a quotient rule. And differentiate the top, leave the bottom untouched, take away, leave the top untouched, and differentiate the bottom. And I take it back. That's why the people who write these get all the big bucks. I don't think this answer is going to be anywhere near as ugly as I thought it was going to be. But let's see if I'm right. E to the 2x plus 3e to the x, take away e to the 2x, all over e to the x plus 3 squared. Hasn't that at least made it doable now, right? It's not anywhere as bad as I thought it was going to be. So, I'm not saying it's easy, but that's a lot nicer than it could have been. Now, we are going to be doing concave up, concave down, so we need to find the second derivative. In other words, we need to differentiate that. I'm going to have to do a little bit of extra work here. I foiled that guy out to get this fella. And you might think, well, normally, why would you do that? It looks really nice there. Well, it looks really nice there for an answer. But if you're going to differentiate something, isn't that going to be easier to differentiate than this? That's the only reason I'm doing it. So, second derivative is now kicking in. It'd be a miracle if they managed to keep this guy together, right? But we'll see. F dash J, take away F of G dashed over G squared. If you differentiate the top, you get 3e to the x, and you leave the bottom alone. Take away, leave the top alone, which is that guy, and differentiate the bottom. If you differentiate e to the 2x, you get 2e to the 2x. If you differentiate this guy, you get 6e to the x, and you don't get anything from that guy. And on the bottom, you get e to the 2x plus 6e to the x plus 9 squared. Yep, it was ugly. Let's see if we can do some style points on it. I'm going to, well, I could do it two different ways. And, I could actually just pull out a common factor, then combine them. Or I could distribute them and then combine them. I don't know which one's going to be easier. So I'm just going to differentiate. I'm just going to distribute. So that guy times that guy is 3e to the 3x. That guy times that guy is 18e to the 2x, and that guy times that guy is 27e to the x. I'm going to multiply these together and then subtract. So I'm going to get take away 6e to the 3x. That times that is take away 18e to the 2x. And it's all over that guy squared. Okay, let's start thinking about making this look pretty. Isn't that guy just him, right? Isn't e to the 2x plus 6x plus 9 actually this guy? So if you take this guy and square it, isn't it really just that guy squared? Are you comfortable with that? So the bottom's not actually as ugly as it looks. Now the top has got a lot of major issues, but let's just collect like terms. Those two guys cancel out, and those two guys kind of sort of blend together. So I've got negative 3e to that guy, and I've 27e to that guy. Okay, it's a little bit nicer, right? Not great, but nicer. I can pull out a common factor of 3. Can I pull out anything else from the top as a common factor? Anything else as a common factor from these two terms? Because there is. Yeah, great. And if you do that, this guy is just left with a 9. And this guy here, yikes, is negative e to the 2x. And I'm going to rewrite this guy a little bit differently. Then that just somehow looks nicer to me, right? I'm picture straightening it. Looks nicer. It's the same thing, right? Okay, we got the derivative. We factored the heck out of it. Step 1. Right? Second derivative, same process. Now we're going to look for critical numbers. And that's going to be when the second derivative is 0 and when the second derivative is undefined. So let's cover that guy up. The only time that you will get that top to be 0 is when 9 take away e to the 2x is equal to 0. E to the x is never 0, right? So that doesn't count. Now, if you want to find out when does this happen, it's going to happen when 9 is equal to e to the 2x. That's going to happen if you take the natural log of both sides, when that is true. And so that ugly value of x is where the second derivative is 0. Undefined will happen when the bottom is 0. But e to the x plus 3 is never 0, because e to the x is never even going to be negative. So there's none of that. So actually, we've only got one critical number to worry about. So here's my number line. I don't really know what the value of that guy is, so let's find out. 0.5 log 9 is about what, 1.1 roughly? Okay, so I'm going to go 0, 1, 2. And 1.1, which is about here, is where a half log 9 lives. And the second derivative is 0 there. And so I need 2 test points, because that's basically guys to the left and to the right. And I'm going to pick, you tell me who I'm going to pick. Who should I choose as an easy to work with test point on the left? What value of x should I use for my test point on the left?
0.
Why not? I don't have a lot of choice here, so I'm just going to pick 2. And now I'm going to find the value of the second derivative at 0 and the value of the second derivative at 2. And again, I don't care about the number bit, just as it plus or minus. So I put a little bubble around it so I don't go in the wrong place. Here is my guy. Right. At x equals 0, 3 is positive. E to the 0 is 1. That makes it positive. 9 take away 1 is positive. And anything to the power of 4 is positive. That means everybody here is positive. Right, so I've done that without a calculator, right? Okay, let's do x equals 2. That might be a bit harder. 3 is positive. E squared is positive. 9 take away e to the power of 4. I'm not convinced, but I'm pretty sure it's negative. That one I will have to do a calculation on. And I was right, it's negative. And that guy at the power of 4 is always positive. Not a surprise, really. Negative. So what do we have? Well, we can now tell you where it's concave up. And that's going to be when the second derivative is positive. So that's anywhere up to the x coordinate of a half log 9. It's going to be concave down. In this case, starting at half log 9 and anywhere to infinity. So basically, you just got half of the shape's happy and half of the shape's sad, right? Which is kind of, isn't it? They've got that cubic look, one up, one down. And what else do I need? Oh, I need to find the point of inflection, right? That's the changeover. Would you agree there's changeover here? So that's going to happen at 1/2 log 9. And if you wanted to know the coordinates, it's a half log 9 and well, I can't tell you the answer because the one that they've got is different from that. But can you imagine plugging that in and getting some value for it? But you would always have to return back to the original function. So let me do them. Oh, of course. Darn it in space. That is the right answer, right? That is the x coordinate. But isn't that also 9 to the power of half? And isn't 9 to the power of half 3? Do you know I could have been doing log 3 all the way through instead of a half log 9? Okay, so I now know that at natural log of 3, and then what's the value? E to the log 3, right, over e to the log 3 plus 3. And do you know that's 3, and that's 3 plus 3, so guess what the answer is? A half. So would you believe it? The coordinates of the point of inflection aren't actually really ugly at all, right? Instead of a half log 9, I should have called it log 3. It didn't change any of my answers, so you agree that this is still correct. It's just that that is nicer looking if you call it log 3. How are we doing, guys? Are we good? I told you this was a long one, but we're really at the end now. So what is left? Basically, the exact same things that we've done. You're going to, I'm not doing them because they take forever, but you're going to get a polynomial where you find when it's increasing, decreasing, max and mins. And then you're going to keep going and doing the second derivative, concave up, concave down points of inflection, right? You're just basically putting both pieces together. And you're going to do that for polynomial and for a rational function and for some weird function with a log in it, but it's actually not that bad. Any questions before we move on here then? Glad to see the end of it. It's a long process, kind of cool, but it gets a bit tedious after a while. So our next topic actually the last one that's official for this week, so we'll definitely get it finished before this week's over, is, let me put the heading down. It is, where is it? 4.4. It's called LHospital. This is using derivatives to find limits. That's what we're going to do. We're going to using derivatives to find limits. So way back in week 1, didn't we do the limit as x tends to 4 of some fraction, and we got the answer by factor and cancel and conjugate method maybe, right? Those types of techniques. Now we're going to show you that you can use derivatives to find limits. In fact, once I show you this, you're going to say, why did we do it the other way when this is so much easier? But you couldn't do it this way, because wouldn't you have to know how to differentiate things to be able to find the limit? And so it's a kind of cart before the horse, right? You have to figure out how to do limits so you can get derivatives. Then you use that to get shortcuts of derivatives. Now that you know how to do shortcuts of derivatives, you can go back to the beginning and find out easier ways to find limits. Kind of little circle life thing on it. Now, before we come to what L'Hopital's rule is, and by the way, it's a formula. That's good, right? Before we get there, let me introduce you to a concept that we need to be aware of, right? And that is called, I'm trying to spell it, indeterminate form. Americans are really nice when I misspell things, because they just think that's the way they spell them in Scotland. But half the time is I just misspell them. Indeterminate form. There are certain calculations that if you're asked to do them, you do not know the answer. That's essentially what an indeterminate form is. They almost always involve zeros and infinities in some combination. So here are the, not all indeterminate forms, but the ones that you need to be aware of. Zero over zero is indeterminate form. Infinity over infinity is indeterminate form. Now you might say, well, how could a calculation like that ever happen? Well, suppose I told you x minus 3, x squared minus 9, and I told you to evaluate that at x equals 3. Wouldn't you get 0 over 0? Infinity over infinity is also indeterminate form. Indeterminate form means you don't know the answer to it. And that could happen, for instance, if I went and said to you, I want you to get x squared plus 1 over x cubed plus x, and I want you to do the limit, say, when x was infinite. Would you agree that would get you an infinity over infinity situation? Those are the two types of indeterminate form that L'Hopital's rule was really developed to deal with, right? Is there an easier way to find limits of expressions, typically fractions, that are in indeterminate form without having to do factor and cancel, for instance, right? Or maybe a conjugate method. And there is. And here it is. This is L'Hopital's rule. It says that the limit as x tends to a, right, so it could be 2 or 5, right, of a fraction, so it's typically always going to be a fraction, is equal to the limit as x tends to a of the derivative of the top guy divided by the derivative of the bottom. Now notice that is not the quotient rule. Isn't that the top guy totally separate from the bottom guy? And you might think, well, you're not telling me the answer. All you're telling me is that you can take a limit and turn it into a different limit. And that doesn't sound like it's very helpful. Well, let me show you it being helpful. If on week 1, I gave you this question, picking you, Charles. If I say, Charles, we're going to find the limit as x tends to 1, and the only method you've got is factor and cancel. Do you really want to factor x to the power 100? Can you imagine how many factors it might be and how hard it would be to find them all? But according to LHospital, you put a little L when you use LHospital above the equals. As long as this is indeterminate form, so let's do our check. If you plug in 1 here, don't you get 1 take away 1 is 0 and 1 take away 1 is 0, right? You get indeterminate form. So according to LHospital then, you can just get the answer by doing this. If you differentiate x to the 100, you get 100 x to the power of 99, take away nothing. And if you differentiate the bottom, you get 1. And this guy is just 100 times 1 to the power of 99, I guess over 1, which is, guess what? The answer is 100. Whoa, isn't that cool? Just differentiate the top and bottom and find the limit of the new fraction. And hopefully the new fraction is nicer than the old one. Right, let's do this guy. The limit as x tends to 3 of x take away 3 over x squared minus 9. Now, if you put in x is 3, you get 0 over 0, indeterminate form. So LHospital says you don't need to find that limit if you want the answer. What you can do is you can differentiate the top and you can differentiate the bottom, and the answer ends up being 1/6. Oh, I mean, isn't that easier than factor and cancel? Cool. How about this one? If you plug in 0 there, you get 0 in the top, 0 in the bottom, indeterminate form. If I asked you to find the limit as x tends to 0 for that guy, would you agree you'd have a problem if you were doing it by week 1's techniques? Let's see what LHospital does. Differentiate e to the 2x. You do get e to the 2x, don't you also get a times 2? Remember, it's a baby general. Differentiate e to the x minus 1, you get e to the x. Now you can plug in zeros. Technically 2 zeros and 0. So, oh, the answer's 2. If you plug in 0, it's 0 over 0, indeterminate form. Everybody is happy. LHospital says differentiate the top, differentiate the bottom, and now you can get the answer, and it's 1. Did you know that the sine of x over x as x tends to 0 is in fact equal to 1? I don't think you could have done that using week 1's technique. I think the best you could do, wouldn't you do a table of values getting really close to 0 and seeing that it levels off at a number that you think's probably 1? That'd be the closest you could do. Oh, before I forget, LHospital also works for infinities. Suppose you want to find the limit as x tends to infinity of a fraction. Then according to LHospital, you can differentiate the top divided by the derivative of the bottom. And the answer to this limit is the same as the answer to that limit. So, suppose I wanted to find then the limit as x tends to infinity of x cubed minus 4x over, x squared plus x. Now, if I plug in infinity, I get infinity over infinity in determinant form. Now, something bad is going to happen here, but there's a fix. According to LHospital, then, you can just differentiate the top and differentiate the bottom. And the answer to this fella is the same as the one you want. Why is this a problem? Oh, if you plug in infinity here, don't you still get infinity over infinity, which means it's still indeterminate? What do you think you do if you're using LHospital and you do it once and the answer's still not solvable? What do you think you can do to get around that?
Do it again.
You just do it again. So the limit as x tends to infinity of 6x over 2, which is basically what? 6 lots of infinity over 2. Would you agree that this answer is infinite? Kinda cool. LHospital, it's one of my kind of favorite little niche market things. By that I mean it does a job, right? But a very specific job. Doesn't it find the limit of certain fractions? I mean, that's what it does, right? So if you want to know the limit of a fraction, LHospital will do that for you, as long as the fraction is in determinate form. So I'm just picking one somewhere. Yeah, let's do this one. This is a version of question 4 homework. And so it's the limit as x tends to 1 of that guy over that guy. If you were doing that week 1, wouldn't you have to factor x to the 5 minus 1? I think you'd have a problem trying to even figure out how you could factor that, but you'd have to. And when you have to factor x cubed minus 1 and then, cancel it, not really feasible. If you plug in 1, you get 0 and 0, so it is indeterminate form. The limit as x tends to 1 then of 5x to the 4 on the top and 3x squared on the bottom. Are we good? Now, in this case here, couldn't I just plug in 1 and get the answer 5/3? Right, 5/3. Now, I know it didn't happen in this question. I want you to imagine that I was doing a question where it was a limit as x tends to 0, right? And it ended up being 5x to the 4 over 3x squared, right? You are allowed to do the following, and it's not LHospital. You are and you should always simplify your fraction, right? If you do a derivative and you've got a nice fraction, oh, wait a minute, I can cancel it down a little bit, do that. And then you can plug in your number and you can see now the answer is 0. If I left it here, wouldn't I be saying 0 over 0 and I'd end up doing lots and lots of LHospitals, especially I'll make it silly. Do you really want to do it for another 20 times? There's no need to if you do a little bit of algebra. And that's quite clever. And now I'm going to show you a strange, annoying idiosyncrasy of LHospital. And it is, if you shouldn't have been using LHospital, right? So it isn't indeterminate form, right? If you shouldn't be using it, but you go ahead and do it anyway. It will work in the sense you'll get an answer. It'll just be wrong. So you got to be careful. Every time you do the LHospital rule, the first thing you should always check is it indeterminate form? Because if it's not 0 over 0 or infinity over infinity, don't go near it. Whatever the answer is, LHospital's not the way to get it. So I'll show you an example of that. Suppose I wanted to find the limit as x tends to 3 of this fraction. Would you agree that this one actually doesn't require any work? Can you just plug in 3 and you get the answer, right? And let's just see what that answer would be. 3 squared add 3 over 2 lots of 3 add 7. That's 12 on the top, 13. So the answer is 12 13s. Agreed? That's the right answer. Now let's suppose that I was doing this question and I just got into that frame of mind. Hey, LHospital, love it. It gets the answer dead easy. Just use it everywhere, anywhere, just use it. Let's see the dangers of doing that. If I use LHospital on that, I would be doing the limit as x tends to 3 of 2x on the top, 2 on the bottom. And that would get me 2 lots of 3 over 2 is 3. Do you see I get an answer, but it's not the right answer? So if you're wondering why every single question I keep checking, oh, is it indeterminate form, right? Is it 0 over 0? The reason for that is, and I don't know if there's one of these in the homework, I hope there is, because, you know, they vary them, so some of you will get this and others won't, you know, just the way the numbers work out. If there's 10 examples, if I stop checking, right, I do the first 9 and it works perfectly, so I get lazy on the 10th one. Isn't Murphy's Law going to be the 10th one? I should have done it because it wasn't indeterminate form, right? So you got to be aware that if you're going to use this technique, make sure that it's 0 over 0 or infinity over infinity, and then use it, and that's fine. But if the answer doesn't need any of that, right? If it's just something you can do directly, right? If it's not 0 over 0, then you shouldn't use LHospital. It's dangerous, not a good place to be. Let's try this fella. The limit as x tends to 16 of the square root of x take away 4 over x take away 16. Would you recognize that as a conjugate method from week 1? Nothing wrong with conjugate, it works fine. It was a good method when we needed it, right? But let's see what LHospital does with it. Right, if you differentiate this guy, I guess I should call it x to the half. You get 1/2 x to negative a half. I know it's a bit ugly, and I need to put in my limit. Let's do it underneath. 1/2 x to the negative a half over 1. Right? Differentiate the top, you get this. Differentiate that, you get 1. I would probably rewrite this in a little bit easier to calculate form. Basically, it's 1 over 2 square root of x's, which you agree eventually that's what it is anyway. 1 over 2 square root of x's. Now I can plug in 1 over 2 square root of 16, 1 over 2 times 4. Guess what? The answer is an 8th. Wasn't that? I'm not sure that's that quick. Would you agree the conjugate method probably would get the answer almost as quickly? But it does do conjugates, doesn't it? It handles square roots, which is nice. Let's do our friend trig. Oh, last question for today. Let's do our friend trig. I want to find the limit as x tends to pi upon 4 of cosine x take away sine x all over tan x take away 1. There is no way in the world you could do that with week 1 techniques, right? Week 1 basically kept away from trig, didn't it? We never did trig, right? LHospital, you can handle it. Can you trust me that if you plug pi upon 4 in here, you get 0 over 0 in determinant form? So LHospital is going to then change this. If you differentiate a cosine, you get a negative sign. If you differentiate a negative sign, you get a negative cosine. And if you differentiate a tangent, oh, you tell me, what do you get if you differentiate a tangent?
Is it negative secant squared?
Oh, so close. Secant squared. The rule for it is if it starts with a C, it's negative. Right, so tangent doesn't start. So if it was cotangent, you'd have a negative in front of it. Now that guy might and does look horrible, but it's actually, you can evaluate it. I got this guy. I got this guy. All over secant squared. This guy. Okay. If you go to your unit circle, the sine of pi upon 4 is root 2 upon 2. So this is negative root 2 upon 2. This guy is negative root 2 upon 2. If you want to find the secant of pi upon 4, it's probably better to find what the cosine of pi upon 4 is, and then just turn it upside down. Well, the cosine of pi upon 4 is root 2 upon 2, so the secant is 2 over root 2, right? Basically, you turn it upside down. So 2 over root 2 squared. You get one of these guys, you take another one away, you've now got negative 2 of them. Well, negative 2 is a half, so you've basically just got one of them. This guy is going to get you top guy squared, bottom guy squared. So you've got negative 2 over 2. There's your answer. And you may want to check some of this because I did zoom through it. But essentially, if you want a secant, a cosecant, or a cotangent, find what the sine is and turn upside down. Find out what the cosine is, turn upside down. Find out what the tangent is and turn upside down. So that's essentially a secant is 2 over root 2. So a secant squared is that guy squared. And if you're wondering where this came from, 2 squared gets you 4. Square root of 2 squared gets you 2. 4 over 2, 2. And the top guy, negative a half, negative another half, doesn't mean you've got negative one of them. And last name,